I'm presenting this work. Unfortunately, my voice is also not good. Maybe have voice frequently. So I'm presenting the work of my PhD student André, which is a joint PhD with University of Brasilia with Araújo. He worked on the fretting fatigue problem, and he tried to include the effect of non-proportional stressing and where to predict the fretting fatigue line. So to tackle this problem, I'll first introduce what is fretting fatigue, and then I'll talk about the way that we model fretting fatigue, and at the end I'll try to share some results that we obtained and try to conclude something from the part of his PhD. Fretting fatigue is happening in a lot of, let's say, common applications in industry. One of the common or classical ones is the railway axis. Here we have the axle, here we have the wheel, and then at contact interface between the wheel and the axis, because of the bending load or because of the fatigue load that we have, at the middle of the contact we have sticking situation, so the two contact parts are sticking together. At the sides we have very micro slip, which is, let's say, dominating the crack initiation and crack propagation phenomenon in that, let's say, particular position. This nice graph was actually proposed in 1988, a very old one, but still can be used to assess the competition between the wear process and the fatigue cracking. What you see here is the displacement amplitude between these two parts in contact. At this side we have fatigue lifetime, at this side we have the wear process. So the blue curve that you see here is the evolution of the fatigue lifetime at different contact status. Here you have sticking, so there is no relative displacement. Here we have kind of mixed slip stick, so it's sticking and slipping, and here we have gross sliding, but here we have fully sliding condition. So what is very critical here is the border between the slip stick and the gross sliding. So then when we are at this slip situation, the fatigue life is minimum. We have some limited wear process, local wear process, but finding the exact point here is very challenging because it's the amplitude that we are talking about is around, this is global actually measurement, is around 10 micrometers. So what are the objectives of this work of my PhD students? So as I said, if we have two contact bodies and we have a normal load, we have a relative displacement between them, and then we have a partial slip condition, which we have stick and slip, and we have gross slides. So if we try to vary the normal load and the displacement amplitude, then we have three different regimes. One is the partial slip, mixed slip, so it starts with the gross sliding but ends with the, let's say, stick and slip situation, and here we have fully gross slide. The critical part for cracking is here. So the fretting crack or the fatigue crack initiates at the partial slip regime. But a lot of simulations try to predict the fretting fatigue crack initiation and propagation without taking into account the local effect of wear process. So what André did in his PhD, he tried to simulate the wear process plus the crack initiation, plus the crack propagation, and try to monitor the effect of wear process on crack initiation and crack propagation, but under partial slip regime. We used some experimental data which we performed a couple of years ago, so you see 9 experimental data here. The axial stress, the normal force was constant, and then there is a kind of ratio between the tangential load and the normal load. So this is the experimental setup. We have a dog-bone-shaped specimen, 2 pads are pushed against the specimen to mimic the same condition that we have in the real application, and 2 compliance springs plus the normal load, the contact load that we have, generates a tangential stress at the contact interface. So the crack initiates at the contact edge and propagates in a mixed mode because of the tangential load that we have, and then further it goes down into the specimen, and then because of the dominant effect of the axial load, then we have a kind of perpendicular crack. This is the typical crack shape that we see for fretting fatigue condition. And here the stress conditions are very non-proportional, so we have non-proportional stresses, and that's the driving factor or force for the crack propagation. But that's also very tricky when it comes to crack propagation lifetime prediction. So to model that, André used in a specimen, a fatigue specimen, a 2D model, a fretting pad were pushed against that, a tangential load, normal load. So we tried to do the mesh convergence study, and we found around 12 micrometer is the proper one which we can count down, and then the area that was interesting for crack initiation and propagation where we refined the mesh, and then the mesh size changed. So we used 4.5 as a coefficient of friction, and we use abacus to simulate that. So to predict the crack initiation lifetime, we try to use the critical distance approach. We use Talemi FS and SWT parameters. We combine that with theory of critical distance to extract data at the critical distance of L, depending on the material that we use. We use this, let's say, material properties. We use aluminum 2024 T3 in that application, and we try this method to predict the crack initiation line. But we wanted to be accurate when it comes to crack initiation lifetime. So for us, crack initiation was around 100 micrometer, which is actually the same size as a grain, 1 grain in that material. So what we did, we had this, let's say, SN curve data for the material in the dogma shape, which is typically the lifetime of initiating 1 millimeter crack. So we tried to fix this by fracture mechanics approach. So then we propagated the crack from 0.1 millimeter to 1 millimeter, and we subtracted the lifetime from this graph to have the crack initiation lifetime of 0.1 millimeter. And then we used this stability and Talemi associate to recalibrate the material parameters that we need for crack initiation lifetime from no damage to 0.1 millimeter crack. Next, we used the R-chart model, and we tried to simulate the wear process both in the fretting pad, also on the specimen, actually at the contact interface. There are two possibilities in abacus. You can use subroutine, but we used in this case Python scripting to do all the things in a single mesh. So we create the model with the Python, and then we try to analyze the data as a contact interface, and then we use wear coefficient, as you can see here. We took it from literature, and some jumping cycles. So the stresses, basically contact pressure and slip amplitude is being calculated at each node, and then we move down the nodes according to the depths of wear that we calculate. And this, let's say, process or this loop is being done till we have the crack initiation lifetime. So this is basically what we did, and we used the minor loop actually to take into account the damage accumulation. He did it because we wanted to also focus on the variable amplitude loading condition. But this is basically what happens. So then we run the test, we calculate the stresses, and then when the damage is being accumulated, it's being combined with the wear profile, new wear profile, and we continue that till one of these elements is failed because of the crack initiation. Next, what we had to do was combining these wear effect with the crack propagation. But as I said, the stresses here are very non-proportional. So we use XFAM in a single mesh, but we try to also come with a new idea how to predict the right crack class using a new technique. So we used, again, the stability parameter, but in 3 different ways. One, extracting that at the crack tip, one at the critical distance, and then again, one, the maximum value of the mean stress, actually stability parameter around the crack tip to find the next kicking angle of the crack. So in that way, we were hoping to be able to capture this non-proportional stressing. And then we compared this data with the available, widely used available criteria in the literature, for example, NTS, the maximum tangential stress, minimum energy release rate, or K2 equal to 0. And just to see which one of these are matching the experimental data and how can we distinguish our new methodology that we are proposing. So here what you see, this is the simulation of the crack propagation in the specimen. This is the experimental curve, and the red one that you see here is the one that we predicted using the stability at the actually critical distance ahead of the crack tip. But what is very interesting here is the other 3 criteria. So then we started and see they are all overlapping over each other. It's not possible even to see, but these 3 common ones, they are all predicting the wrong path because they don't take into account high non-proportional stressing that is happening at the crack tip near the contact area. So with this technique, we could somehow be close to the experimental data that we observed. So we try to apply that to other tests from 1 to 9, and we see almost the same behavior for all of them compared to the experimental data. Then we separated the crack initiation from the crack propagation lifetime. When I say crack initiation, I mean up to 0.1 millimeter. And then we more or less saw that around 85 to 90% of the total lifetime is spent in the crack initiation lifetime. So the crack propagation is a small part of the total lifetime. Here, what you see is the worn profile. So as I said, we try to simulate the wear on, let's say, on this pad and also on the fatigue specimen, and that has a big influence on the stress distribution at the contact interface, even if we have partial sleep region. So what you see here is the first cycle without any wear, and then this is the last cycle with the wear. This is the contact pressure distribution at the contact interface between threading pad and fatigue specimen. So that gives us the idea that the crack initiation lifetime, the stress distribution, all these things would be affected by this wear profile. Also, the crack propagation lifetime could be affected. So what we saw here, you see the with wear and without wear simulation. The pulse is almost the same, but the number of cycles are different. And if we include the wear process, the number of cycles are less. So then we have less number of cycles, including the wear process. And then we try to plot that against the predicted data. So here what you see, the predicted number of cycles, here the experimental one, and here you see the data without taking into account any wear process. So we tried these two criteria, the multi-axial criterion, without any separation of crack initiation or crack propagation, and it's a direct calculation, and we see that they are almost in the plus minus 2 times of the experimental data, but some of them here, for example, the stability is underestimating the data, and we try to do that, separate the crack initiation and crack propagation, but not taking into account any wear process. It was better, so you can see that, especially for the stability parameter, it's getting better, closer, and in this case for photoemitters, it's also inside the band that we have for plus minus 2. And then we try to do that again with wear process. We selected only a stability parameter in this case, and then we have here the stability parameter for crack initiation and crack propagation without wear, and here with wear. And what you see here, that especially at the low stress levels, at high stress levels and low number of cycles, the effect of wear process can be seen. So then we have better prediction if we include the wear process even at the partial sleep regime. So I think that's a short summary of part of the André's actually PhD. So we try to include the wear process on crack initiation and crack propagation. We could propose a new criteria which takes into account the effect of non-proportional stressing for crack propagation, and he also tried to validate that, and it worked. I think that's it from my side. This result has been published already last year, so if you're interested, you can take a look at our last publication. I don't know if I am on time or not.
Yes, you are. At least thanks for sharing your friends with whom you can.
Yeah.
Any questions? Yes, please.
On my presentation. So experimentally, this crack actually goes more, initially let's say at 45 degrees, and then it goes more vertical, and then it starts going back actually. Like why? I don't think you
I don't know what
you don't have that in simulation, right? So what?
I will tell why.
So why is it happening? That's the question.
If I have access to my slides, it could be. But okay, I can give you explanation. So what you saw that in the experimental, okay. So you were talking about the experimental observation. here basically.
Yeah.
This is what you're working. Actually, this is the important part that you're focusing on. It's 2 times of the contact area. So the A is the semi-contact width, and from here to here is the crack is being governed a lot by the combination effect of normal load and tangential load. But when it passes this point, it's being governed by the axial load, and there is no effect or very minor effect of contact. But the point is here, when you have the crack propagation under axial load, so the grain distribution also plays a role. So this is not a typical behavior. We see that in, for example, other let's say samples that it can go like this or like that. So it's mainly following the grains, let's say, distribution.
Thank you.
Thank you. Another question?
Well, thank you for the presentation.
Yes.
And about, can you comment about the friction model? Because your message is about, please consider where, because it has importance. How do you model the friction contact?
Yeah, it's as I said, we are using our construction. We are using the Lagrange multiplier as an algorithm, and the coefficient of friction of 4.5.
And what about the wear rate?
The wear rate, we took it from literature, so it's 5.81 10⁻⁸. So that was for 2024. It's good that you brought it up. I'm not suggesting that you have to take into account wear, because maybe it depends on the different. Maybe it doesn't have that much effect, but it has an effect. Because the idea was that the wear could not postpone the crack initiation under partial slip regime, but in this study we showed that it has a minor effect. It has an effect, so it's not that it doesn't have any effect. But does it worth to spend time and simulate that for partial slip? Depends. Depends on the application, depends on what you want to use that model for.
Okay, we have time for another one. Yet another question, but no questions anymore. Thank you, Reza.